Every time you send a message, stream a video, or load a web page, data travels across a global network of cables, routers, and servers in milliseconds. But how does your laptop in New York talk to a server in Tokyo without losing a single bit? Computer networks are the invisible infrastructure powering the digital world. Today, we demystify the entire stack, from the physical cables at the bottom to the applications you use every day at the top. The OSI model, Open Systems Interconnection, is the 7-layer framework that defines how data travels across networks. Layer 1 is physical, raw bits over cables or wireless signals. Layer 2 is data link, frames between directly connected devices, handled by your network card. Layer 3 is network, IP addresses and routing, how packets find their path across the internet. Layer 4 is transport, TCP and UDP, reliability and flow control. Layers 5 and 6 handle sessions and encoding. Layer 7 is application, HTTP, DNS, email protocols, what your apps actually speak. Think of it as a team passing a package down an assembly line, each layer adding its own envelope before transmission. TCP and UDP are the two workhorses of internet transport, and choosing between them is one of the most fundamental decisions in network programming. TCP, Transmission Control Protocol, guarantees delivery. It establishes a connection via a three-way handshake, breaks data into numbered packets, confirms every packet arrived, and retransmits lost ones. Perfect for web pages, emails, file downloads, anything where accuracy matters more than speed. UDP, User Datagram Protocol, fires packets without confirmation. No handshake, no retransmission, no guarantee. But this makes it blazingly fast. Video calls, online gaming, live streaming. These use UDP because a slightly dropped frame is better than waiting for retransmission. The golden rule: use TCP when data integrity is critical, UDP when speed and low latency matter more. DNS, the domain name system, is the internet's phone book. When you type google.com into your browser, DNS translates that human-readable name into the IP address your computer actually needs to connect. Here's the journey. Your browser checks its local cache first. If not found, it asks your operating system. Still nothing? It queries your ISP's DNS resolver, which asks a root name server, which points to the authoritative name server for that domain, which finally returns the IP address. This entire lookup typically takes under 50 milliseconds. DNS enables the entire web to function without humans memorizing IP addresses. It's also a frequent attack target. DNS spoofing and cache poisoning can redirect users to malicious sites, which is why DNSSEC and DNS over HTTPS exist. HTTP, Hypertext Transfer Protocol, is the language of the web. Every web page you load is a series of HTTP requests and responses. HTTP 1.1 established persistent connections and chunk transfers. HTTP 2 brought multiplexing, sending multiple requests simultaneously over one connection, dramatically reducing load times. HTTP 3, built on QUIC rather than TCP, eliminates head-of-line blocking entirely. HTTPS adds TLS encryption on top of HTTP, ensuring your data can't be intercepted in transit. The TLS handshake authenticates the server's identity using certificates and establishes encrypted communication. Today, HTTPS is the baseline. Browsers mark plain HTTP sites as insecure, and search engines penalize them. Traditional HTTP is request response. Your browser asks, the server answers, connection closes. But what about real-time applications, chat, live dashboards, collaborative editing? This is where WebSockets shine. A WebSocket connection starts as a regular HTTP request, then upgrades to a persistent, bidirectional channel. Both client and server can send messages at any time without the overhead of new connections. This enables true real-time communication with minimal latency. Slack, trading platforms, multiplayer games, and live sports scores all rely on WebSockets. The alternative, long polling, where the client repeatedly asks, "Any updates yet?" is inefficient and creates unnecessary server load. WebSockets are the right tool when you need the server to push data to clients instantly. REST and GraphQL are the two dominant approaches to designing web APIs, and understanding their trade-offs is essential for any developer. REST, representational state transfer, organizes data around resources. Each endpoint represents a thing, /users, /products, /orders. It's simple, widely understood, and stateless. But REST often causes overfetching, getting more data than you need, or underfetching, requiring multiple requests for related data. GraphQL, developed by Facebook, solves this with a single endpoint where clients specify exactly what data they want. One query can fetch a user, their posts, and post comments in one round trip. This is powerful for complex frontends. The trade-off: GraphQL has higher learning curve, more complex caching, and can expose sensitive data if not carefully secured. Most large applications use REST for simple external APIs and GraphQL for complex internal data requirements. Computer networks are the foundation of everything digital. Understanding TCP versus UDP helps you choose the right protocol. Knowing how DNS works helps you diagnose outages. Grasping HTTP evolution explains why some sites load in milliseconds. These aren't abstract concepts. They're tools you use every time you build or debug a networked application. As you go deeper into software engineering, networking knowledge becomes your superpower. It separates developers who guess from developers who know. Keep building, keep learning, and keep asking how the data gets from here to there.